So far, our discussion of vectors has been a geometric interpretation of vectors. And what that means is when we want to talk about vectors so far, we need a picture of the vectors. And that's all we have to work with. Anytime you want to get away from a graph or a diagram, then you start to talk about algebra. So today we're going to define what it means to talk about vectors algebraically. The idea being that we want to work with vectors and we don't want any to have to refer to a diagram or a picture. How do we do that? Well, we should probably start by deciding whether our vectors exist in two-dimensional space or three-dimensional space, and we're going to cover both. We'll start by assuming that they exist in two-dimensional space. That means that the vectors can be drawn on a flat surface. Examples of flat surfaces, the monitor that you're looking at right now, the whiteboard in our classroom, a piece of paper, that kind of thing. We refer to that as two-space. And in vectors, we'll have a shortcut for two space. We'll say R2. Now, you don't want to get that confused with R squared. It's R2. And actually, R2 is often written like this. I have trouble figuring out how to type that, but sort of a fancy looking R with little 2 refers to two space. So let's start by assuming that our vectors exist on a flat surface. How can we talk about them algebraically without the need for a picture? Well, it's quite simple, actually. We just use the Cartesian plane or the XY plane. So here's an example. I've got the Cartesian plane here, and I've got two vectors. Now the trick is that vectors, they don't have position. They just have direction and magnitude. That means they can be moved around. So I can take a vector and I can move it so that its tail is at the origin. If I do that, the head of the vector, I'll do that with this one too, tail at the origin, the head of the vector will land on some point. And that point will then uniquely define the vector. For example, this one looks like it's the vector could be 6, 3. This one, it looks like 1, 2, 3, 3, negative 2, or around there. So I can describe a vector just really by giving a point. For example, if I say that vector negative 5, positive 1, there's only one vector that can be negative 5, positive 1. That's the vector that lands on negative 5, positive 1. That's this vector right here. If I'm able to draw it, that means that the point negative 5, 1 has completely determined the vector's magnitude and its direction. So just to summarize that, if V is a vector in R2, or 2 space, the vector V can be plotted on the Cartesian plane such that the tail of V is at the origin and the head of V falls at some point with coordinates AB. V can now be described by the point AB. When described this way, the vector is known as an algebraic vector. A and B are called the components, or sometimes the vector numbers of this vector. If you've taken grade 12 physics, you've probably taken vectors and broken them up into their horizontal and vertical components, in which case you're basically kind of doing the same thing. The only thing you're not doing is interpreting that as being some point on a graph. It's basically the same. So that's why we sometimes call it as components. Now the next part isn't super important, but I will bring it up here. Sometimes we might refer to point AB as P, and then if we want to talk about, we can still talk about a point-to-point vector. We could say the vector OP is the vector formed on the Cartesian plane from the origin to point P. I'll just show you what I mean about that really quickly. So what that means is that if this first vector right here at 6, 3, if we call this point P, this is the origin, and hence this vector could also be referred to as vector OP in case we want to talk about point-to-point vectors. Don't worry too much about that. That'll become more clear when we need to deal with vectors that way. So in this example, we're given vector A, which is an algebraic vector, and we're asked to find its magnitude and direction. So, I mean, the magnitude, you might want to find the magnitude of algebraic vector, so it's useful to be able to do that. And when you find its direction as well, it's almost like you're kind of finding, giving a geometric interpretation of this algebraic vector. So let's just start by sketching it. If it's at negative 7, 2, that means that it lands on the point negative 7, 2. So it probably looks something like that. Or, of course, this point right here is negative 7, positive 2. Okay, so let's start with the magnitude of A. And how do we calculate that? Well, it's not that difficult. If you look, you've got a triangle here where this side, this side is 2, and this side here is 7 or -7. And we can use Pythagorean theorem to solve for the hypotenuse, which represents the length of the vector or the vector's magnitude. So the magnitude of a squared is equal to 2 squared, or you know what, you can use -7 squared if you want, plus 2 squared. Now, I realize that that's kind of strange. Why square -7? Why not square +7? Well, they're both 49. The other thing, too, is I'm doing it that way to basically saying, hey, look, every single time you do this, you can square the x and square the y, and that will give you the square of the magnitude. Okay, 49 plus 4 is 53. Take the square root. The magnitude of vector A is the square root of 53, whatever that is. Now, as we're doing that, let's move on to the general case. For any vector, let's say let V, we'll use V, let V equal vector AB, algebraic vector. The magnitude of V will always be equal to the square root of A squared plus B squared, just from Pythagorean theorem. So there we go. Now let's move on to the direction. Now there's no the only thing we have to reference a direction is the XY grid. So how do we talk about direction? Well, it's standard practice to talk about the direction the vector makes with the positive x-axis. And we usually call that angle theta. That's the standard way for talking about angles on the Cartesian plane anyways. So the angle it makes with the positive x-axis, I can figure that out using, well, I mean, I have the hypotenuse now, but I'll use tan because I don't need the magnitude. So the tan of theta is equal to -2/7. So I can use inverse tan to figure out what this angle must be. So this relationship gives me the angle. I do have to be a little bit clever and know that, look, it's going to be an angle that's obtuse. It's not going to be the reflex angle, okay? Because you know, tan theta equals -2/7. There's an angle there and an angle down there. If you were to, you know, punch that in on your calculator just as you see it, you're probably, I think every single calculator is going to give you -16 degrees. Well, -16 degrees is, of course, down here. That's not the actual angle. If you did ignore the negative sign, you get +16 degrees. So we know that it's really 180 minus 16. So it's about 164 degrees is what we call that angle. So then, in general, this is all part of the specific case. In general, we could say that the angle, the tan of the angle, it is always going to be B over A, where theta is that angle it makes with a positive x-axis. So that's how we can describe, you know, the general direction of an algebraic vector. We don't do that a lot, but we do it sometimes. Okay, now we move on to 3-space. We live in a 3-dimensional world, so we should probably be able to talk about 3-dimensional vectors. They can't all be drawn on a flat surface. Now, interestingly enough, if you have just 2 vectors, you could always draw 2 vectors on a flat surface. But as soon as you introduce a third one, they may or may not be in what's called the same plane. Okay, so let's talk about that. Now, in order to represent 3-dimensional vectors, we actually need a 3-dimensional coordinate system. So the XY plane is no longer good enough. So we're going to use, big surprise, X, Y, and Z. It might be a little surprising that it takes this long in math for you finally to talk about a 3-dimensional coordinate system. You're in the final math class of high school. And that's just the way it is. It gets pretty confusing when you start talking about plotting things in 3 dimensions and functions that need to be plotted in 3 dimensions. So we do start with vectors. So how do we do that? Well, like I said, we use X, Y, and Z. Now, what we normally do when we draw it, the easiest way to think about it is we kind of think about like the x-axis is coming out of the page, and then the y-axis traveling horizontally, and then Z being up and down. So if you can imagine this in 3 dimensions and imagine this X popping out of the screen, that's Y. and that is equal to Z. I mean, that's one possible way of drawing it, and I would recommend, I always do it that way. If I'm sketching the three-dimensional coordinate system, that's how I do it. So you can kind of think about x, y as being, this flat surface, this plane that's perpendicular to the screen right now, and y and z are on the screen. That might be not obvious. Maybe you think z is the new one. It should come out of the page and not x. You can do it that way as long as you follow some rules. I don't recommend it. It's not usually done that way. As long as your coordinate system passes what's called the right-hand rule, it's okay. I'm going to try to explain what that means. If you curl the fingers on so take your right hand out. If you curl your fingers from the positive x-axis to the positive y-axis, then your thumb needs to point in the positive z direction. And then your coordinate system is valid, and all the definitions that we give in vectors will work. Okay, so although there are other ways to draw these, that's how I recommend doing it. You could imagine it this way too, the right-hand rule. Imagine you have a piece of graph paper on your desk, okay, and you draw the x and y axis the same way you normally would. Curl your fingers from the positive x to the positive y, and that means that the z-axis would have to come out of your desk, not down, but up out of your desk. So that's another way you could imagine the three-dimensional coordinate system. Don't make it more difficult than it is, though. I think that this is the best way to think about it. And once you've done that, you're ready to talk about three-dimensional vectors, and they're the exact same as two-dimensional. A vector in 3 space has no position. It can be moved wherever you want. So take any vector and put its tail at the origin, and it's going to land on some point in 3 space. And in this case, we need not just a and b, we need a z value as well. So we have 3 vector numbers, or 3 components for a vector that exists in R3, a, b, and c. And yeah, they're hard to sketch. I mean, you can imagine a vector here, trying to figure out, what vector is that. Your textbook does a bit of this, and you can go ahead and look through and see how they draw vectors. I'm not going to make you go through a lot of that, especially not teaching online. It's hard to draw three-dimensional representations on a flat surface. So the next question we might have is, how do we calculate the magnitude of a vector if it's in 3 space? Maybe I gave you the vector 5, 2, 4. How do I calculate what the magnitude of that vector is? Okay, let's just take a look at a picture. Imagine you've got a vector and its corner, okay, so what you can imagine doing, is drawing a rectangular prism. Okay, so just like so. Here, imagine it this way. Imagine the vector is already there. So there's my vector. And my vector is, let's say, the vector ABC. So it lands at point A, B, C. This is the x-axis, the y-axis, and the z-axis. Okay. So I draw the prism, the rectangular prism, so that this is A, okay, this is B, and the last missing dimension is C. What that does is that makes the vector what's called a body diagonal through the prism. Remember we talked about body diagonals of cubes? It's the same idea, okay? And we can use this. So this is kind of like in the other example with 2 dimensions. We drew this little it's almost like a rectangle here. I did it as a triangle, but it's kind of like a rectangle. If I were to fill in the rectangle, now it's a prism, a 3-dimensional rectangle. Okay, so what we're going to do is we're going to figure out the length of this vector in terms of A, B, and C. So what we need to do, we'll start by thinking about this face diagonal right here and calculating its length. So it is on, actually, can I back up just a bit? I apologize. I've labeled this ABC incorrect. Okay, B and C are mixed up. So B is let's put B right here. B is the amount you travel in the y direction, and C is the amount you travel in the z direction. So that's C right there. Okay, so we're using A and B. We can calculate this using Pythagorean theorem. This is a right-angled triangle because, of course, there's a right angle right here. Okay, this is A. I'll draw B again right here. And this is B. So this right here, I'm going to call that D. D d is equal to the square root of, or let's actually do it this way, sorry. D squared is equal to a squared plus b squared, just from Pythagorean theorem. Okay, so I'll call that d. I better label it d. Okay. There is another right angle triangle I'm going to work with, and it has D as one side and C, which is this side right here. So it's this triangle right here. Okay, I'm actually going to highlight it here for you. It is this triangle right here, here, and here. And there's a right angle right here. This triangle isn't, this is like the base, okay, of the prism. This triangle is kind of like sitting up. It's perpendicular to the base, and it's kind of sitting in the middle of the rectangular prism, if that helps. So it has this length D as its base. There's a right angle right here. This is the hypotenuse, and this side right here, which is C, the amount we travel in the Z direction. It's not B. B is the side right here. So it's C. So really, this right here, which is also the vector's magnitude, this is vector V. So now I can say that vector V squared, using Pythagorean theorem again, is equal to D squared plus C squared. So D being one side and C being the other. But D squared is really just A squared plus B squared. So that means that the magnitude of V squared is equal to A squared plus B squared plus C squared. And we get basically the exact same formula as in 2 dimensions. The magnitude of V is just the square root of A squared plus B squared plus C squared. Okay, you just add the C in there as well. Okay, let's talk about the direction of a vector in 3 space. And this can be a little confusing, but don't get worried too much about it. So in 2 space, we gave the angle that a vector made with a positive x-axis. We could have, if we wanted to, we didn't, but we could have given both angles, the angle it makes with the x-axis and the y-axis. That would have been redundant. We don't need both angles. In 3 space, though, we do actually decide to use all 3 angles, 3 different angles. So the angles that a vector makes with the positive x, y, and z axis. As it turns out, we're going to learn that if you have 2 of these angles, you actually don't ever need the third. Okay, you can figure out what it would have to be. But for now, let's just think about all 3 angles. Okay, so that angle, an angle that a vector makes with the positive x, y, or z axis can be anywhere between 0 and 180 degrees. It can't be more than 180 degrees. And it's kind of like if you imagine, it's hard. I mean, in class right now, I literally pull some rulers out and start showing angles between lines. But I mean, when 2 lines intersect, there's always some angle they create. It's almost like it's the smallest angle that you can make in 3 space. Okay, so although they might be tilted kind of weird, if you imagine like sort of the flat surface formed by two lines in 3 space, it's that angle that's made on that flat surface. So it's very hard to see this with diagrams. I'll do the best I can to explain it. We're probably going to ignore this one for now. I've got an online tool we can look at too. Oh, by the way, the angles are called alpha, beta, and gamma. Alpha being the angle it makes with the x-axis, beta with the y, and gamma with the z. In this one, it sure looks like this vector is kind of going into the page because alpha looks so big there. So alpha looks like it'd be bigger than 90 degrees. It's an obtuse angle there, formed with the positive x-axis. So let's take a look at beta, for example. Based on my interpretation of this, and it is an interpretation because a 3-dimensional picture like this, you can't tell for sure what's going on. You just kind of guess that it looks like we could fill in a little triangle like this. Oh, sorry, let me try that again. Little triangle like this. Best I can, like that. And this is a right angle, okay? Notice that in this example, there's my right angle. In this example, they've chosen not to draw a y perfectly horizontal on the page, just to kind of give it a 3D looking aspect. But there is a triangle here where this is the vector. So let's say this vector is v. Here's vector v. Okay. And notice that we've got the angle beta as part of this triangle, and this is the component in the y, which they've called y as opposed to b. It doesn't matter. Let's actually change that. We'll call it ABC. And so this is point B. Sorry, this is B. Okay, the amount you travel in the y direction. So as it turns out, the cosine of beta is equal to B over the magnitude of V. So I can use that formula to calculate the angle that this vector would make with the positive y-axis. Just take its y value and divide by its magnitude. That gives you the cosine of the angle. The same is true for the other two angles as well. In this particular picture, it's just harder to see. There it is. Now, these alpha, beta, gamma, those are what's called the direction angles, okay? And the cosine of those are called the direction cosines. So let me just sketch that for you. Alpha, beta, gamma, direction angles. Whereas these right here are called the direction cosines. Now, the nice thing about direction cosines is when you're talking about the intersection of two lines, something like this right here, the angle, the cosine describes the angle in its entirety. So let me just back up and see what I'm trying to explain here. If I were to tell you that rather than give you like an angle, I could give you the cosine of the angle, and from that you could figure out what the angle would have to be. And the reason that's true is with cosine that's true, because with cosine, if the angle of intersection of two things has to be between 0 and 180. So from cosine, you know the angle. Since the cosine in quadrant 1 is positive, and here it's negative, you don't have to worry about the cast rule. For example, if I gave you the sine of an angle, you wouldn't know if the angle was here or here, since sine is positive in both quadrants. With cosine, you don't have that problem. You always know which one it is. I'm not sure if that made any sense or not, but I'm not going to worry too much about it. This idea of direction angles really confuses students. This picture is hard to interpret. Usually they can kind of see the first one I've done for you, beta, just because this picture kind of spells it out nicely. It's a lot harder with the other two. As it turns out, direction angles aren't super important. Direction cosines are actually more important, and we'll see why. I'm going to pull up one other tool on the internet for you to look at, though, before I move on. Okay, so this is part of the coursework for University of Waterloo. It allows you to enter a vector's coordinates in, let's say, and you have to do positive ones. Let's say 3, 6, 2. Plot. Okay, and it shows you vector 3, 6, 2. It fills in a little triangle there for you. Little rectangular prism for you. And then you can actually see the angles. I might make these a bit bigger so it looks a bit better. Let's go 5, 7, 4, and try that. Okay, a little better, yes. Okay, and I can look at alpha. And it tells you the angle. It fills in that little triangle for you, which is kind of helpful. So that's what I wanted to show you. So you can see that this vector, there's the angle that it makes with the positive x-axis, and you can see the triangle. So the cosine of alpha is a divided by the magnitude of the vector. I can do the same thing for beta. Okay, so here we go. So you can see, if I just twist it around here, there's angle beta, and there's my vector, and so the cosine of beta is the y direction, b divided by the magnitude of the vector, and you can see it for gamma as well. So there it is right there, the angle it makes with the positive z-axis, okay, and the cosine of gamma, okay, is going to be the c value, which is right here, divided by the magnitude of the vector. Now, I'm not sure what's going on with the magnitude, why it's 0 here. That's not correct, but something wrong with that. Anyways, you can play with that if you want. If it's really bothering you that you can't figure out or can't visualize direction angles, but I'm telling you, it doesn't matter that much. We're going to learn that the easiest way to talk about the direction of a three-dimensional vector is just give another vector that has the same direction. So don't worry too much about that right now. One important formula that we are going to talk about is the fact that if you take the sum of the squares of the direction cosines, that will always equal to 1. In the next lesson, we're going to learn why it is that this formula has to be true and why direction angles aren't as important as we might think they are. And for one last example today, we're given a vector 3, 5, negative 4. Describe the vector by its geometric characteristics, then verify the square of the direction cosines do in fact have a sum of 1. So we can start with the magnitude of v is going to be equal to the square root of 3 squared plus 5 squared plus negative 4 squared, which gives you the square root of 50, which is, of course, root 50 is root 25 times root 2, so we just get 5 root 2. Okay, so there's our magnitude. And we can also talk about direction. The cosine of alpha is equal to 3 divided by 5 root 2. The cosine of beta is equal to 5 divided by 5 root 2. And the cosine of gamma is equal to negative 4 over 5 root 2. So you can see that for the z-axis, the angle it makes with a positive z-axis is going to be bigger than 90 since the cosine is negative. Okay, that's why cosine is more useful than, say, sine. And that's not surprising because there's a negative z direction. So the vector kind of goes, if we think about z being up and down, the vector goes down. So it makes a more than 90-degree angle with the z-axis. From there, we can easily figure out what the angles would have to be. Now, of course, 5 over 5 root 2 is just 1 over root 2. Hey, there's an easy one. Beta is 45 degrees exactly. We use our calculator as fine just to get approximate values for the other two. I'll do that now. And I'm getting about 65 degrees and about 124 degrees. Sorry, my head's in the way there. There we go. And the final thing to do is verify the sum of the direction cosine, the squares of the direction cosines do in fact have a sum of 1. In fact, these direction cosines, they're a better way of talking about the angle because these are rounded and these are not, well, except for this one. These two are rounded. And like I said, next lesson we'll learn why the direction cosines are actually a little more important. So if I take the sum of the squares of these, what do I get? So I have 3 over 5 root 2 squared plus 1 over root 2 squared plus negative 4 over 5 root 2 squared. And what do I get when I figure that out? Well, 3 squared is 9. Okay, 5 root 2 squared is, well, root 2 squared is 2 times 25 is 50. Plus, okay, I get 1/2. And then I get 16 over 50 again. Okay, well, that's 9 over 50 plus 25 over 50 plus 16 over 50, which sure enough is 50 over 50, which is 1. Exactly what we expected, exactly what the formula told us we would get. Again, next lesson, we'll learn why this formula works. Why is it that always happens?